Now, what if conduction is not through a flat wall but through a cylindrical wall? Normally, we encounter flow of heat into a wall which is cylindrical, normally through pipes, heat transfer through pipes, and other vessels. Now, heat more or less here, instead of heat flowing from here and going to the other side, in this case, heat is radially flowing through the inner area of this pipe towards the outer surface. Okay, like we could think of like heat is flowing from the inside out. Okay, but essentially not just to this outer end, but sort of heat radially flowing from the inside to the outer surface. Okay, and when we say here, and the difference here in the flat wall conduction is that cylindrical wall has a variable area of heat transfer. That's because here, as heat flows through here to this part, the area is A, and until it exit to the other end, the area where it flows still A. But in this case, the area where the heat flows while the heat still in the inner radius of this pipe is smaller, and that area is just given by this one. The area where heat flows is through the surface of this inner shell, like it's like a tin can of radius here, r inner, and the heat flows to the surface, okay, to the surface of this, and the area here, like we call that the inner area. In this case, area inner is just equal to the circumference 2 pi r ri in this case times the length. This could be thought of like of length L. So that will also have a length of L times L. Okay, and as it flows outward, the shell or the cylinder that it you know the area gradually increases, and as you can see, as it exits to the outer surface, the area is now quite big. The heat will now need to pass through this large surface area, okay, because the diameter now of the shell is quite big. And if we see it now, this one will now have like, shall we say, of the outer radius. The inner radius is Ri, and the outer radius here is Ro. And the area now where the heat need to pass through will then just be equal to 2 pi Ro, the circumference of this circle times what? The length will give you the surface area times the length L. Still the same length. However, since R is bigger than Ri, clearly the area where heat flow is bigger on the outside, while here, while it's still on the inside, the heat needs to flow only to this small area. Now the thing is, when heat flows, it's the what? It's the Q that is constant. It's the amount of heat flowing is constant, but the area is changing. So things will be more or less a little difficult than the flat wall. However, in our analysis for cylindrical wall, it will turns out that this condition will still lead to the same equation that we could use for a flat wall. And I will write here the equation that we can use for flat wall. Same. Q is equal to delta T over R, where R now is just somehow modified from this. So for cylindrical wall, we can then use this same equation that we have derived for the flat wall. I'm not be doing a lot of derivation as of the moment. You can look at the book really, and if you want, I don't want to make this discussion really longer, because what I would like to show here is how could we just treat this um, two types of flow of heat into the flat wall and cylindrical wall, unify them as a single concept. Now, Q now will just be equal to delta T over R. But now, if you'll say, what will be the R then for a cylindrical wall? Well, in analogy to the flat wall, R will just be equal to, instead of delta X, the thickness of this slab, Well, the thickness of this pipe will just be given by what? Thickness, or delta R, the difference in the outer and the inner radius. And then the K will still be K, the conductivity of the pipe. Anyway, that is, if this is made of steel, then this must be made of steel, then they must have the same K. Not a big problem with that. But the real problem here may perhaps be on what A to use. Here, the area is constant for a flat wall. That area is the same as the area on the left-hand side. But in this case, now the area in the inner will just be way much smaller than the area of the outer shell. So what area will we use? Well, of course, we may think of, well, we can use some average area. In this case, allow me I will try to convince you that the best way to do this without much of a derivation, or perhaps I may be deriving that in the next video, that the area will just be an average, a form of the average of the inner area and the outer area. In that case, it's equal to area log mean or logarithmic mean. Nothing really special with log mean. Simply, area log mean is just the logarithmic average of the two areas, and that is just given or can be simply solved by the equation area log mean simply area inner minus area outer over ln of area inner over area outer. This is just the same or similar to arithmetic mean, but this is just, shall we say, logarithmic mean. I'm not really deriving that as of the moment, but there's nothing special with area log mean. Like if this is area, this is just area, but just the average of the area, logarithmic average of the inner area and the outer area. Of course, we know how this is derived, right? And of course, we can consult books or other videos for that. And this leads us now to the unification of the idea of a flat wall conduction and a cylindrical wall conduction, that the equation that we can use on these two is just the same. The rate of flow of heat, Q, is just equal to the difference in the temperature. Temperature here of the inside T1 and the outside T2, the same T1 and T2. And the resistance is very much the same. Instead of delta X, the thickness of the wall here, still the same thickness, but in this case it's cylindrical, thickness will be delta R. And K will still be K, the conductivity of the material. And area, instead of area here, which is a uniform area or constant area, here we have area which is just the logarithmic mean between the inner area and the outer area, which is not that difficult really to calculate. If you know the radius and the length, then it will just be simply given by this one, 2 pi RIL. The inner and the outer will be 2 pi RO times the length. And things will just be simpler if you only have, or if you need to memorize only same equation for flat wall and a cylindrical, this one for a cylindrical wall. Not much really of mathematical complexity. What I'm trying to show here is, well, if we could think of this as one, then why not? Thank you.